This is Steve Edford again. I want to talk about general relativity and why it does not cause gravity. Okay, it's because, all right, now, first of all, the explanation of how gravity works, the standard explanation I hear, is you take a rubber sheet, you stretch it out in a horizontal plane, stretch it out tight, you place a bowling ball over the rubber sheet, it creates a dimple in the rubber sheet. Now, if you take a tennis ball and roll it at the right angle and the right velocity, right at the edge of that dimple, the dimple will capture it and it'll start rolling around the bowling ball. This represents an object like the moon orbiting around the Earth. That's gravity by general relativity. Okay, now the problem here, all right, first of all, let's have a little bit of fun here. I like doing this. So the explanation for how gravity works is stretch out the rubber sheet in a horizontal plane, you place a bowling ball over it, it makes a dimple, and then the dimple creates the gravity. So now you see what happens here is you stretch out the rubber sheet, you place the bowling ball over the rubber sheet, gravity pushes it down, makes the dimple. The dimple in turn creates gravity. So what came first, the gravity that created the dimple or the gravity that the dimple created? Okay, that's just poking fun at that analogy. But I can give you a better analogy of what they're talking about warping space, even though I don't believe in it, but this is a better analogy. Now, if you take a block of foam rubber, of low density foam rubber, and you take some fiber optic lines and you feed them through and parallel to one another through all three axes of the foam rubber. Now, if you take a hollow metal tube, you put a balloon over the end of it, and you seal it at the top end of it. Now, if you put a little metal cone-shaped thimble at the end to protect the balloon, you pierce the metal tube with the balloon into the foam rubber. Now you blow compressed air through the metal tube, it inflates the balloon, and it deforms the foam rubber from within inside. When it does, it's going to bend those little fiber optic lines in all three axes, not just one. It'll bend them in all three. But now that doesn't mean it causes gravity. That just means that it warps space and makes light bend around it and all that kind of silly stuff. But anyway, that's all that is. But now let's look at general relativity. Now, the way I got some diagrams, that'll help some. So here, this is a cross section of the bowling ball, the tennis ball, and the rubber sheet. The rubber sheet is deformed down here. Even the tennis ball will make its own little deformation in the in the rubber sheet also. But now what you have is this is supposed to represent warp space, and now you have force, I guess, of gravity or whatever. A force is pushing the tennis ball down, and when it does, the rubber sheet gives a reaction force because Newton's law of motion, every reaction has an equal but opposite reaction. So it's exerting a force from an angle here, in which you have a vertical force which offsets this force, and then you have a horizontal component that's pushing the tennis ball toward the bowling ball. So now if this were the Earth and this were the moon, then this were space, warp space, then when the moon is pushing down, warp space is pushing the moon toward the Earth. So how can that happen? I'd like for somebody to explain to me in rational terms how warp space, which is not made of any kind of matter, how can it interact with matter and push the moon toward the Earth? So bottom line is general relativity does not cause gravity. Now, it might warp space if they think so. I don't think you can. You can't warp space. Because I've come up with a little principle of mine that you can take any kind of matter. I just use with air. It's like with air, you can displace air, but you cannot occupy it. But with space, it's just the opposite. You can occupy space, but you cannot displace it. So meaning that you can't warp space. You can occupy it, but you can't push it aside. Like the Earth cannot warp space, push it aside like that. It's going to occupy the space. That's all it's going to do. So anyway, that's why, I mean, it's in simple terms. But not only that, but this little example here where they have the rubber sheet is actually touching the bowling ball. But now if space were warped around the Earth, space would warp down here like this, to where it would be equal distance all the way around. Because space is not two-dimensional, space is three-dimensional. You're going to have warped space coming all the way up around here too. So now what you have is the moon is here, just like see now the tennis ball here wants to roll down the inclination of the rubber sheet into the bowling ball. It draws together like gravity would do. But down here, you have the tennis ball here and the bowling ball there. The tennis ball is just going to roll down here around the bowling ball. It's not going to go toward it. The same with space. If this is space, this is the Earth, the moon is going to roll down this little valley here, and it's going to roll around and around the Earth. It's never going to touch the Earth. It's not approaching the Earth. It's just rolling around it. And the only thing keeping it from flying away, see now, there's something there that as the moon orbits the Earth, centrifugal force wants to make the moon fly away from the Earth. So according to Newton's law of motion, if you can't oppose that force of that centrifugal force with an equal but opposite force, the moon is going to fly away. So since the moon does not fly away, something applies that external force to push the moon toward the Earth. That's so general relativity says. But now if you watched my previous video of quantum gravity, you would find that nothing is pushing the moon toward the Earth, but the Earth is pulling the moon toward it. While at the same time, the moon is pulling the Earth at the same time also. But anyway, there's not a whole lot to that. It's just real simple. It's unbelievably simple to explain away general relativity. They can come up with all their technical mumbo jumbo about, well, relativity this and tensor mathematics explains that and whatever. It's all meaningless. If they can't produce that force to keep the moon from flying away from the Earth, general relativity does not cause gravity. That's just the bottom line. So anyway, that's it for that. My next video is I'm going to do the same thing with special relativity because it's not so special anyway, but it's going to have to cover more material because there's so many different aspects to cover on special relativity. But that's about it for general relativity.